Okay, I stopped the last times on this example, which is the beam with 2-point masses, M1, M2, okay? And this is, we call it accelerated circular motion, okay? When you see this problem here, yeah, um, the things here we apply first, yeah, as we talked about to determine the forces and so on. We have either the, the Newton's second law or the D'Alembert method. Yeah, this is what we do. The first things we do it with the application of the second law, that we do the cutting free the individual masses, calculate the cable forces, and investigation of the equilibrium of the beam. Normally, you should know this problem that we say that when we do what we call to cut the free individual masses, this is, I think you have done it in mechanics 1, okay, to determine the internal forces when you have applied forces on the system, yeah, then the second law, D'Alembert fictitious force, allows direct formulation of the dynamic equilibrium, okay? That it means this one with the second Newton law, we have to, let's say, make the cutting free the individual masses, and this D'Alembert fictitious forces not need this cutting free the individual masses. And this is, if we look like this now, what we have, if we take the inertia forces, yeah, in D'Alembert, which is opposite to the coordinate of the motion x1, x2. Now what we take? We take what we call the local coordinate system, okay? Local, that is means for each motion, we have the mass m1 and we have the mass m2. Then we imagine that the motion is in this direction. Then if I draw, then you will get such motion, yeah? I draw approximately. That it means it's rotating around this point O. Then it means we will get here, let's say, I will draw it. Then we get here certain angle, and it's the same angle here. This angle here will be the angle phi. Okay, then it means that the mass m1, yeah, the position of this point here move to this position, okay? And the position of this point here move to this position, yeah? Then what we have as external forces, we have the force F, which is applied on this part here, yeah? This, let's say, yeah, make the system, or let's say the beam, yeah, rotating around this point O. And now what we have, we imagine that is when it's this point here move to this position, then we have x1, okay? We take the coordinate system, local coordinate system, let's say, as it's one directional problem. Why? We say that there is only small displacement. Yeah. When it's small displacement, in this case, there is small rotation here or small angle. Okay. Then we have x1 here and we have x2 here. Yeah. In this position, there is the velocity x dot 2 and there is also the acceleration. Now, as external forces, we said we have the forces F, which is horizontal, and we have two vertical forces or external forces, which are the weight G1, yeah, which is the mass M1 multiplied by gravitational acceleration, and we have G2. Okay. Now what we do the dynamic equilibrium of moment about the point O. Okay. Then it means what we have here, we have the forces. If we take this global coordinate system, okay, we have X and Y direction. And of course, we add, yeah, you know that we have the Z axis. If we take this like this, yeah, the point here in outward here, this is will be the Z. This is will be Z here. Then it means now, if we look to the position that we have F multiplied by the arm, yeah, you know this in mechanics 1, the arm here, it's only to the point O, it's only H, yeah. When you look here, you make the rotation and the method of the hand, yeah, or finger direction will give that the rotation is opposite to Z. Yeah, it's outward. In this case, we have here minus F multiplied by H. This is the moment due to the forces F. Now, if we look to the G1, yeah, G1 multiplied by the distance here, L1, okay, then in this case, it's in the same direction as Z. Then it will be positive. You take the for here, the weight G2, yeah, G2 will rotate, yeah, in the same direction as for the force F, yeah, this will create the moment negative, here minus G2 L2, and we have the two forces due to the acceleration x dot 1 and x2 dot 2, and this is, we call them as internal forces, yeah, due to the acceleration. In mechanics 1, in static, these terms, the two last terms are equal to 0 because we assume there is no acceleration. Yeah, the system is static, it's not dynamic. Okay. If we choose now the global coordinate system, this is, we took the two masses. Okay. We cut this system here. Okay. Then it means we have the cable here and we have the cable, second cable here for the mass M2. In this case, we cut this one here, like you make here. This is we do. You cut here, you cut here, okay? And you isolate the two masses, okay? When you isolate the two masses, Then in this case, what we have the forces on the cable, okay? It's only, let's say, when we take this global coordinate system, the masses here will be the forces here. It's M1 Y1.11, okay? And it's the same masses on the opposite side here for the cable which is attached to the beam. Then either you use these terms when you isolate, when you take the global system, or you cut the free cut here, okay? You take in this case these two terms. Instead to use these two terms here, you take these two terms, okay? Then you are, let's say, free to choose which method, okay? Now what we have here, as we said, this point here move to this position. Let's say, as we said that here, we imagine like this. Then we have here the angle phi, okay, will be also phi dot and phi dot dot. The same here, you have phi dot and phi dot dot, okay? Then it means you have the position here, the velocity x dot 2 at this position here, this point move to this point, let's say B, and you have here B prime. The same here, let's say A and A prime, okay? Now, if we look to this distance here, x1, okay, the cover distance, let's say, of this point here, for example, A, in this case, we take only the tangent of phi dot, okay, and phi dot, the tangent phi dot will be only x1 dot multiplied by divided L1. This is will be phi dot. As we said, when you have small angle, okay, and this is the case, we do it, yeah. In small, there is only small vibration or that. Then the covered distance, let's say for this case of the system, we said that tangent any angle phi or phi dot or phi dot dot, yeah, will be equal to the value of this angle or this velocity or acceleration. Then it means we have in this case here equivalently to say tangent phi dot, it's x1 dot multiplied divided by L1, and tangent phi dot will be equal to phi dot. Okay, this is small, let's say, yeah, velocity or small angle or small acceleration. The same principle we do it for the second part. Yeah, we have the same here rotation, let's say. This part here will be x phi dot will be x dot 2 divided by L2. Okay, then we have the kinematic relation between the velocity at this point and the velocity at this point here. That is means we have phi dot now is only x1 dot divided by L1 from this relation, and will be equal to x dot 2 divided by L2, yeah, for here this relation. The same principle, what we have, we can here make the relationship, yeah, the acceleration x dot dot 1, okay, from this relation. Now the acceleration will be only x dot dot 2 L1 divided by L2, okay? When we make here, we make only the time derivation, yeah, of this. When we have here, we have x dot 1, it's equal to L1 divided by L2 multiplied by x dot 2. Then we have the velocity here, and then we make the time derivation, then we get the acceleration. When we get this acceleration, okay, we are on place either, yeah, x dot 1 here, or you make the inverse, you make x dot 2 as function of the x dot 1. And when you do this, okay, you're on place here, you will get x dot 2, yeah, by this relation here. Okay, it's only we replace it x dot 1 as function of x dot 2, okay, and we get now this relation. Now, if we do it for the global coordinate system, that is means on the beam, in this case, we take y dot 1, okay, instead to take x dot 1, we have the same relation, yeah, for this point here, A. Here, the same principle, y dot 2, we take with minus because we say the y direction, yeah, is upward here, then it means it's opposite to the direction of y, yeah. Then we take the sign minus here, and the same principle, we get v dot, the same y dot 1 divided by L1, which is equal to y dot 2 divided by L2. We get also in the same as for the local coordinate system. Let's say here we take or the relation, we get the relationship between y dot 1 and y dot 2, yeah, and we are in place in the same principle here. The same method we are in place here in this relationship, yeah, and we get the same expression. Now, for comparison, there is solution with the second Newton law. We do the free body diagram, that is means of both masses. Then we make the cut, okay. When we make the cut here, now we isolate the mass M1, okay. When we isolate the mass M1, what we have G1, the external forces, yeah. We don't look to the beam. Beam, it's somewhere here, okay. Then when we isolate the two masses, when we have the cable force S1, okay. This is the internal. For the beam should be somewhere here, and you have the other forces S1 here, opposite to this one, yeah. Then we make it opposite to get the equilibrium at this part here, and the same principle for the second part, which is, let's say, what we called, the point B. Now, if we make the equilibrium of these forces, what we have the forces, the sum of the forces. In Newton case, we said the sum of forces, it's the mass multiplied by the acceleration. This is the second Newton law. Yeah. Now we do this, what we have as external forces. We have S1, which is in the same direction as the axis X1 minus G1. Okay, will be equal to the mass M1 multiplied by the acceleration x dot 1. Then we have the expression for S1, okay, from this relation here. The same principle, we use it for the mass M2. The sum of the forces, yeah, in x2 direction is equal to the mass 2, yeah, multiplied by the acceleration here. In this case, we have the direction in this, yeah, downward here. Then we have G2 minus S2 equal to the masses, and we have S2 here. Okay. Now, these forces, S1 as S2, yeah, are applied on the beam. here somewhere. Yeah. Now, if we take the beam now, we have S1, S2. Okay. This is the two forces. Yeah. Um, let's say in the cables. Now we do the same procedure. We make the sum of the moment equal to 0, okay, at this or on this point here, O. Then we have S1 multiplied by the distance L1. This is positive, yeah. Why? We said that it's inward, that it means if you use the hand, okay, the finger direction, now you get the S1, the moment due to the S1 is positive. We have the second force S2, okay, it's negative, it's turning like this, okay, and you have F, which is the applied force F here, it's minus F. The moment due to F, it's only minus F multiplied by the arm here, H. Okay, this is equal to 0. From the previous example, we have the relation S1 here. We have the relation for S2. Then we replace the two expression S1 and S2. Then we get the relationship here. The same principle. This is equation is the same as we got here. Okay, from when we use the D'Alembert method. This is the same relation. Now we come always to kinematic relation. That is means the kinematic relation we have x dot dot 1 has not to do this relationship. It's kinematics problem, what we have done in part 1 and part 2. This relationship between the acceleration for the mass 1 and the acceleration for the mass 2. Okay, we have the same relation and has not to do with D'Alembert or Newton. In this case, we replace only the relationship here between x dot dot 1 and x dot dot 2 and the same relation here. In this relation here, x dot dot 1, we replace it by as function of x dot dot 2, and we get the same expression as this one here. Okay. Now you tell me if in the exam I will either specify use the two methods, or I say use this method, either D'Alembert or either Newton, or I let you free. Okay. If it's not specified, then you are free to choose which method is convenient for you. Okay, now coming to the what we call the vibration. What we have here, we have the pendulum. Okay, the pendulum making oscillation, like this. And this position here, it's it's at rest. Let's say a rest position here. Now, if we look what we have the massless rod, the connection between, let's say, the roof or the fixed point to the mass. Okay, we say this part here, it's massless, has no mass. We look only to the mass here, to this ball, let's say. Then we have here attached frictionless hinge to one end. That is means here we have the hinge or fixed point. This is here to the other end point mass, let's say here particle. Okay, it's not body. When we said point mass, that it means there is no radius, or yeah, it's only one point. Okay, what it happens inside, we look only to the acceleration, let's say, sorry, the velocity, position, and so on. For the body, this is we see it, yeah, later. Okay. Then we have free motion in the gravity field with g acceleration. That is means we have only here g acceleration on the earth. Okay. Then we make what we call the mathematical pendulum. Means now, if we look here now, this pendulum here, what it happens on the mass m, okay, as it's rotating, okay, the simple way that it means that we have the angle phi here in this direction, in another direction when it's here oscillate. Then we have the angle phi, we assume it. We have at rest, that it means at time t equal to 0. Okay, this is the rest position here. We have the length of the rod, okay, L. We choose this polar coordinate system, okay, ER, the unit vector or basis vector, AR, and EV, which is perpendicular to it. Now what we have the external force, okay? The external force is only the weight and multiplied by the gravitational acceleration, yeah? Now if we cut this part here, we look what it happens. We have the rod forces, S. Okay, I not always the rod force S. Yeah, this is the notation for the rod force. And to be honest, it's German, yeah, notation. Then we make here S, okay. Then it means on this part here, if I draw it, it's like we have done it for, yeah, the beam, the previous example. Then it means we have here our hinge, okay. Then we have our rod. We cut, then it means we make cut here. Then we have here what S, okay, this is the force S on the rod, and we have the mass here. Here we have our mass M, and we have here S. Okay, when we cut here, then it means that we have S in one side and S in another side. Otherwise, there is no equilibrium. Okay, this is when we cut, but it means we have two forces. Okay, we try to choose always the tractions, yeah, that to avoid, yeah, the negative or the compressions. Let's say we use always the traction. That is means, yeah, we have always traction in the direction of the rod. In this case, that here we have S, okay, this force here. This is the rod force. This is what we do always in static, okay? But additionally to this, things what we do in mechanics 3 or in dynamic, we include now the two forces due to the acceleration. In our case, we have ER, which is the acceleration in radial direction or tangential direction, and we have E phi, which is the acceleration along, or let's say circumferential or circular acceleration. Okay, then it means now why we choose this direction. We said that here, example, that in the lumbar we use always the forces is opposite to the direction of the motion. That is means we have ER now in this direction. We choose the force Ft. We noted it by Ft, the D'Alembert or inertia force. It's opposite to the direction of the axis ER. The same principle. We have if phi here in this direction. We choose the forces which is opposite to it. Okay. Now we isolated the mass m, the particle here m. What we do, we do the equilibrium. Okay. Now we have circular motion with r, which is equal to L. Why we do this? Okay. I told you we have done this expression. If you remember ER, okay, the acceleration in radial or circumferential direction, we said that we had already the expression of this two. The opposite here, we have R, it's only L in our case. Okay, that if you remember, okay, I will try to remove this part here to have better view. Now what we have, if you look now to the expression what I gave, in the first part as well as in the second part of the slides, PR it's only minus L v dot square. If you remember, we say it's only R cross omega cross omega. Okay. The tangential one or the circumferential one, it's only R cross omega dot. Okay. And this is, we get, as we said, R in our case is only the distance here from this point to the coordinate system. It's only L. Okay. Then we have now the acceleration here for this two here, AR and EFI. Now we make the sum of the forces, the dynamic equilibrium, following the Lambert method. The sum of the forces along the radial direction is equal to 0. What we have, in radial direction, we have the weight mg. We project it along radial direction as well as circumferential direction. Okay. Then we have mg cosine phi in radial direction, and we have mg sine phi around along the phi direction here. Additionally, what we have along radial direction, then S, it's opposite this weight force and the D'Alembert or inertia force. Okay, the same principle, we do it along phi direction. Then we have mg cosine phi minus S minus the inertia force in our case is MER. This is equal to 0. Okay. Now, for the circumferential direction, this is the sum of the forces, phi equal to 0. Then we have mg sine phi plus m e phi is equal to 0. Okay. From this relation here, we get the forces S. Okay. It's only expressed by this here, where ER, remember, it's only L phi dot square. Okay. Phi, we said it's only L phi dot. Yeah. Then we get here the equation of simple harmonic motion. Okay. Then we get here phi dot dot. Okay. From this expression here, it's only G divided by L. multiplied by sine phi. We said that here there is small, yeah, motion. Then it means we have here sine phi is equal to phi, as well as what we have done it previously. Tangent phi is equal to phi. Yeah, when you have small angle, when we say linearization, yeah, then it means that here we make that sine phi is equal to phi as well as tangent phi is equal to phi. Yeah. Then we say have here the equation of simple harmonic motion. That is means here if we take this one, sine phi is only phi. Then we have here, yeah, let's say the differential equation. Okay. The variable phi upper as function of time. Yeah. Right side is equal to zero. That we call it free harmonic oscillation. That is mean the second term here is equal to zero. Okay, when the second term is equal to zero in differential equation, we say that here is the free harmonic oscillation. Now, coming to the solution of this differential equation, yeah, and I hope you have done the differential equation in mathematical form, okay? Then we have here the solution always it's like this, okay? Phi t, yeah, phi as function of time, it's given always like this, A sine omega t, okay, plus B cosine omega t. Now, if we look here, we have phi dot, that it means now the, let's say, the velocity, okay, it's the time derivation of phi. Then we derive normally, yeah, A sine omega t. The derivation of the first term will be A omega cosine omega t. Okay. The second term here, B cosine omega t. The derivation with respect to time will be B omega, yeah, with minus sine, yeah, sine omega t, sinus omega t. Now coming to the acceleration, or let's angular, okay, acceleration. This is minus A omega square sine omega t, that is mean the time derivative of this term and the time derivative of this term. What we have here, we have two constants, A and B, okay? And this can be determined by the initial condition. That is means here now. If we look to the equation of simple harmonic, yeah, or free harmonic oscillation, then we have phi dot dot, and we have phi. Okay, what we have to do only to replace phi dot dot by the expression of the by the solution of the differential equation, and the same for phi. Then we replace here for phi dot dot these two terms here, what we got here, okay, and we replace phi by its expression, what we have here. This is will be equal to zero. Now, equating the coefficient, that it means what we have here, differential equation is identically satisfied if now. If we look here now, okay, we are on place here, G divided by L will be omega to omega square. Why? Because we have always in vibration, or let's say oscillation, we have always this expression phi dot dot plus omega square multiplied by phi. is equal to 0. The same principle, if you have x dot dot plus omega square, x equal to 0. Okay, this is always the expression, yeah, for the case of oscillation. That is means we have omega square here is g divided by L, which is omega square here, this term, which is multiplied by phi. Okay, this is omega square here. Then we get to the omega. Then we got it, this is omega, the oscillation frequency. Okay. Now, A and B have to be determined by the initial condition. Okay. Now, if we look for time t equal to 0, this is at rest, phi is equal to 0, and let's say velocity v is equal to v0 because we give certain velocity, which is tangent to the motion, yeah, that making the pendulum oscillating, yeah. Then we have phi at time t equal to 0 is equal to 0. Then what we have to do, it's only to replace it here. Okay, at time t equal to 0, we have sine omega t is equal to 0. And we have a multiplied by 0 plus b. When we replace the time t equal to 0 here, we get cosine omega t is only 1. Okay, then we have here a 0 plus b multiplied by 1. Then we get the value of b. Okay, the constant. The velocity at time equal to 0 is v0. Means we go now to this relation here. Okay. Now we have a omega cosine omega t minus b omega sine omega t. We replace t by 0 in the velocity. Okay. Where we have the velocity here, v0 is only L phi dot t at time t equal to 0. Why? It means that here, as we have the pendulum, when we have the pendulum like this, let's say, we have the velocity here, let's say in this direction, okay. I try to throw it better, yeah. We have here the velocity v0, okay, and at rest here, we have here the angle phi dot, okay. We have this distance here, the rod, yeah. For the rod, this is only L, okay. When we make it, we make the tangent phi dot, yeah, it's only v0, let's say, yeah, divided by L, okay. We say we have small oscillation, that is mean tangent phi dot is only phi dot, yeah. We get this relation here. V0 will be L phi dot, yeah, but phi dot it's at time t equal to 0, okay. Then we have here, we get the value of phi dot, we replace it, it's only v0 divided by L. Then we have phi dot here. We have the relation for phi dot is given by this equation here, okay. Then we replace only time by t equal to 0. In this case, we have here a multiplied by 1 multiplied by omega. Omega is given by this value here. This is the Earth oscillation frequency. The same for the second term here. Sine omega t will be equal to 0 as time t is equal to 0. Then we have here phi dot, Then we have here, then in this case, v0 divided by L is equal to a omega multiplied by 1 minus 0, then we get the value of A. Okay. Then we have the two constant A and B. Yeah. One moment, I remove this part here. Then we have here, if we replace A by its value, okay, B by its value equal to 0, then we get here for the distance, let's say, as function of time of the angle phi, it's given by this expression, and we have the velocity, it's given by this expression. Okay. Then we have periodic oscillation, which is repetitive motion. Yeah. Harmonic vibration, that is means sinusoidal history. Then in this case, if we look, that it means we have here this describing omega t, or let's say phi versus omega t. If we look what it's describing here, the motion or the oscillation, yeah, it's always sinusoidal motion or harmonic motion. And this is, it's repeated, yeah, and definitely, let's say. Then we have here, in this case, the amplitude of the pendulum swing phi max here. This is, you can see it here, okay? It's V0 divided by square root GL, okay? The period here, it's only omega t. Then we have the maximum or maximal angular velocity, phi dot, yeah? It's V0 divided by L, and this is phi max multiplied by omega. Phi max, it's here. Yeah? The period now of the oscillation, that it means we have omega t, okay? It's equal to 2p. That is 2p. That it means this is sinusoidal. That it means when we're making 2p here, we get here at p, yeah, or pi. Okay, this is at 2p, and after this, it's repeating here for t, yeah, and for pi, and here after this 6 pi, and so on, yeah, and this is will be oscillate indefinitely. Then we have here the period, let's say t, which is always, yeah, maybe you have seen it, it's 2p, 2 pi divided by omega. This is the period of the oscillation. Okay. Now we have the number of vibration per second. This is what we call the frequency of vibration. Yeah. When we have the unit, it's hertz. Then we note it by 1 hertz. It's 1 divided by second. And this is, you have the period. It's only 1 divided by the frequency. Okay. And we get here from this expression, when we have here t, okay, given by this value, then we get the frequency is only the square root of g, the gravitational acceleration divided by L divided by 2p. Okay. Now we take the case of other initial condition. Yeah. We imagine that we have at time t equal to 0, we have initial angle phi 0. Okay. We use the same equation. Phi as function of time, it's A sinus omega t plus B cosine omega t. As always here, only we have to replace, yeah, phi 0, okay, when we get phi, and we have here sine omega t by time t equal to 0. We have 0 plus b1, okay, then we get b, it's phi 0. For the velocity at time t equal to 0, we imagine it's 0, okay? Then we have phi dot, we replace it, we get here a equal to 0. When we replace here phi dot, we say it's only, yeah, v0 divided by L, okay? v0, we imagine here it's equal to 0, okay? Then we replace it's 0, then we get this value, we get E equal to 0, then we have the two constant now, A and B, okay? When we substitute, we get this two expressions for phi and phi dot, okay? This is will be here now. The amplitude, let's say it's V0, phi 0, okay? And for the period here, omega t, okay? Then we get here, um, let's say omega t, okay? We are on place as we have done it previously, yeah? Omega t is equal to 2p, and we get here now, let's say, the period, and after this, the frequency. And now if we combine the two, okay, the first one and the second one for the initial conditions, then we get at time t0, the pendulum has an angle phi0 and a speed or velocity v0. We get here now phi t, it's always the same equation, E sine omega t plus B cosine omega t, to determine the two constant, yeah, A and B. We replace, yeah, phi dot by the from the initial condition, phi is equal to phi 0, okay? Then we get here b is phi 0, v initial velocity is v0, okay? We're replacing the expression of the velocity, then we get here phi dot, and we determine a, okay? Then we have now a and b, then we replace in the equation of phi and phi dot. Then we get here the expression for phi and phi dot, okay? And then the same principle, okay? Here we have only, if you look at the two previous cases from the two initial conditions, that's when we had, where we had the phi, yeah, equal to 0 at time t equal to 0, and we had velocity. The second case is the inverse. We had phi, but velocity is 0. When you make the superposition of the two, you get this case here. Yeah, when you look at the expression, that is means this one for the first case, and this one is for the second case. Okay, this is what we get now as expression for this case of spring, let's say. Now coming for this case here for spring vibration, okay, where we have here the spring, and we have the mass or the particle, yeah, with the mass m. Then we have the point mass m. It's at the end of a massless spring. That you imagine that it's the mass of the spring is neglected, yeah, which has the stiffness c. Okay, we have frictional motion of a defined rest position. That is means here, if there is forces here, okay, on the mass, there is only the contact force. Yeah, we neglect, yeah, the force due to friction, yeah, which is in the direction of the motion. Yeah. Then we have a mass oscillator. It's very important in the application. You can find it, yeah, in the machines, auto, and so on. Now, if we look to the representation of this, yeah, as forces and so on, we imagine that we have the initial, yeah, the attached point here. We have initial position L0. Okay, the spring has the stiffness C. Okay, and we have now we take this direction X. Okay, then it means now what we look here. This is the initial condition at rest, let's say. And now we let this spring, yeah, oscillating, let's say, or vibrating. In this case, we have certain distance, yeah, x, which is the position, the new position. We make here, let's say, the cut. When we cut here, okay, somewhere, what we get the spring force, okay? It depends on the which direction, okay? When you look here, you have the compression, okay, at this position here. And then you have traction, okay? That it means you have here elongation of the spring, okay? And here you compress the spring at this position here, this time. Now, if we make the equilibrium with D'Alembert inertial force, okay, we have always this spring law, which is called also Hooke's law, okay. We have the force versus the position x of the spring, okay. We have always this linear relation. That is means F is always expressed as C multiplied by the position. This is, we get here the linear relation between the force and the position. Okay. This is, we said that C is constant factor, or let's say, as we said it here, this is the stiffness C. Now, if we make the equilibrium correlation, we said by D'Alembert, we have the sum of the forces, yeah, is equal to 0. In this case, what we have here, we have when we cut the system here, okay, we have minus C multiplied by X. This is the force in the spring, okay. And what we have the inertia force, or D'Alembert force, which is opposite to the motion, always, yeah. Then we have here minus m multiplied by the acceleration, x dot dot, is equal to 0. Then if we make here now the differential equation, what we have here, x dot dot plus c divided by m, x is equal to 0. Now this c divided by m, it's only omega squared, okay, always, yeah. Now, this is the general equation, okay, we call it harmonic equation, yeah. This case, we said that x dot dot plus omega square multiplied by x is equal to 0, okay, as we have done it before, phi dot dot plus omega square phi, okay. Now, omega, now here, from this expression, okay, it's only c square root of c divided by the stiffness divided by the mass m. The solution, always, okay, x, it's a sinus omega t plus b cosinus omega t. But this means this is the solution of this differential equation. It's given always by this relation here, yeah. We make the time derivative, we get the velocity, okay? From the velocity time derivation, we get the acceleration, okay, by this. Now we have two constants, A and B. A and B can be determined, yeah, by the initial condition, okay? The substitution of x dot dot here and x, okay, and this equation, harmonic equation, then we get the following relation. Initial condition at time t equals 0 at rest, the mass m is released from state of rest at x 0. Yeah, in our case, it's only L0. Okay, at this position here, let's say L0. Now, if we look now, x time t equal to 0, it's x0, this is the initial condition, and we have the velocity x dot at time t equal to 0 is equal to 0. Okay, now if we look to the expression here, what we have x the position, a sines omega t plus b cosine omega t. We are on place now by the time t equal to 0. We have x, which is x0, and the time t0, yeah, we give here 0 and 1 for sine omega t and cosine omega t. Then we get b is x0, okay? For the expression of the velocity, x dot is given by this relation, okay? We are on place now, the velocity is 0, okay? Cosine omega t and sine omega t. Then we get the value of a is equal to 0. We substitute in equation of motion, then we get x is equal to x0 cosine omega t. Okay, as we have here, a is equal to 0 and b is only x0. Okay, then we have here the period of vibration and frequency. The period of vibration is always 2p divided by omega. Okay, omega in our case here, it's only square root of stiffness divided by the mass. Yeah, for this case here, or this problem. The frequency is always 1 divided by or the inverse of the period. Okay, then we have here at the period here 2p. Okay, we have here the amplitude, which is x0. Okay, as for the previous example. Now we take the case of vibration of the mass in the Earth gravitational field. Okay, then we had previously the spring, which is, let's say, vibrating horizontally. Okay, now we take here the case when it's the vibration in the Earth gravitational field. Now we take here the case of unstretched spring. That is means here we have the length of the spring at rest, it's L0. Stiffness is always C. Okay. Now, if we take the static state, yeah, that is mean there is no vibration, okay, or no oscillation. This is what you have done, yeah, in mechanics 1. Okay. Then we have the mass, yeah, moves, yeah, along x direction, let's say, at this position. When we make here the cut, okay, if we make the cut, what we have the weight mg, okay, and we have the force or spring force, which is C multiplied by delta L0. Okay, this is the elongation of the spring. Yeah. Then we can make the equilibrium condition. The equilibrium condition will give the sum of the forces is equal to 0, and the sum of the forces, what we have mg, okay, minus c delta L0, yeah, this is equal to 0, yeah. But at any arbitrary position, okay, when we have the motion now, or the dynamic motion, in this case, what we have now the D'Alembert or inertia force. The motion here is along this direction, okay? Then we have m multiplied by the acceleration, x dot dot, okay? Opposite to this direction. This force, inertia forces, is added, yeah, in this case. Additionally, what we have, when we have here, this is at rest, that is means we have initial elongation delta L0, okay, due to the static, but the dynamic here, we have additionally x, okay? Then we have here always C multiplied by the elongation, yeah, of the spring. The elongation of the spring now it's only delta L0 plus x, okay? Now what we have here, in static equilibrium, in state of rest, we have mg minus c delta L0 is equal to 0. Okay. In this case here, we have the two forces here, the weight and the spring force. But in dynamic, we have this three forces. Okay. Now, for the dynamic equilibrium with D'Alembert inertia forces, we have the sum of the forces Fx is equal to 0. In this case, we have the weight, the force in the spring, and here the inertia force or D'Alembert force. Okay, then it means now with the static equilibrium condition, it follows that minus Cx, when we replace here now delta L0, okay, by its expression here, okay, we have x dot here, okay, then we get here x dot dot plus c divided by m multiplied by x equal to 0. In our case now, here when we look, same differential equation as without gravitational field. But it means either you are in gravitational field, this case here, okay, or you are in this case here, you will get the same equation. You look here, okay? This is C divided by M, okay? It's only omega square. That is means for the second, for this problem, you will, if you have the same initial condition, okay, we'll get the same, yeah, relationship for x, x dot, and x dot dot. Now we have here, we imagine that here, this is the static state that we have x. Here, arbitrary position, in dynamic case, we have F, which is C multiplied by X, and we have here mass multiplied by the acceleration. This is the inertia force. We make the equilibrium, okay, and we have here X dot dot plus C divided by M multiplied by X, the same equation, okay? Now, briefly, but I will return back, okay, to this case. We use now what we call the momentum of particle. From the second Newton law, okay, we have here the forces can be described by the time derivative, yeah, of the momentum here, and the momentum is defined by the mass multiplied by the velocity. Okay. Then we get here, if we have the initial, in case of F, the force is equal to 0. Okay, there is no forces. In this case, the momentum B, it's only the mass multiplied by the velocity is constant. That is, means that there is no change in the momentum with the time. Okay, it will be constant. The initial condition, it's like the final condition or intermediate um, condition. Now, if the force F is different from 0, then we have F multiplied by dt, it's equal to dB, and this is d, the derivative of the mass multiplied by the velocity. Okay? Now, if we integrate from the initial condition, initial time or initial case to an intermediate or arbitrary time, then we make the integral of the forces, yeah, the same for the momentum, dB, okay? Then it means what we have here, these terms will be equal to momentum at actual position minus the initial position, okay? Then the principle of momentum will be, yeah, given by this formula. The integration from the time t0 initial condition to the actual um, condition or actual position is the integral of the force, yeah, with respect to time, is equal to the difference between the momentum at the actual time minus, okay, or the difference between the actual time, the momentum of the actual time, and the initial, yeah, time. This is the expression, the general one, yeah. Then we say the change in momentum, okay, of a system in a given interval of time is equal to the total impulse acting on the system in the same interval of time, okay? Now, there is some simple case. Okay, this is the general, what you have seen here is the general equation, okay? But it's depend, yeah, on the problem. The problem can be simplified, yeah? The case where the mass is constant will not change, yeah? During the motion, the mass will not change. There is no loss of the masses or additional masses, okay? In this case, what we have here, if we do so, that we have the time derivative of the momentum, B, or the change of the momentum here, and V, the mass is constant, yeah. We put it out of the derivation, yeah, as is constant, that which means it's time independent. In this case, we have M is dV divided by dt. By definition, the time derivative of the velocity is only the acceleration, okay? Then we have the momentum for the case of F is equal to 0. Yeah, there is no impulse, there is no forces. B is constant. Okay. Then it's me for the second case, when the force is different from 0, in this case we have M dV. Okay. We integrate, okay, with respect to time. Then in this case, the mass is kept out of the integral. Then we have here, we integrate from the initial velocity to the actual velocity. Then we have the principle of momentum in this particular case where the mass is constant, okay? It's only the mass multiplied by the difference of the actual velocity with the initial velocity. Okay. Now, let's say we take this example, we take this particle or this mass. Okay. This mass, yeah, act on it, this force. And this force, yeah, it's varying with the time. It's time dependent. Okay. Now, if we take the initial condition, the velocity v0 at time t equal to 0 is equal to 0. Okay. Additionally, there is only the contact force in vertical direction, yeah, between the ground and the mass. It's frictionless motion. That is means the R force, which is mu multiplied by N, yeah, this is will be equal to 0 as the friction is equal to 0. Okay, there is no force, yeah, between the ground and the mass, yeah, due to the friction. Okay, there is no force. Time variation of the force. Now, if we look to the time variation of the force here, we imagine that it's here the force at versus or as function of time here, t. This is the period t, okay? We imagine that it's describing this motion, this relationship, okay? Now, the principle of momentum, we say we integrate from 0 to the period t here, capital letter T, okay? The mass, okay, we said we imagine it's here constant. Then we have mass from this expression here, this one, okay? We have the mass multiplied by the difference between the actual position, the actual velocity, and the initial velocity. The initial velocity, we said it's equal to 0, okay? Then we have the mass multiplied by v1, the actual position, actual velocity. Now, if we make the time integral of the force, yeah, it's only the hatched area here of the force diagram. That is means if we look here, it's only triangle, and this is it's only the half of the maximum of the forces F here. We take it as F bar, okay, divided and multiplied by the time here, T, okay. Then we get here the velocity v1 is only the half of F multiplied by time t divided by the mass. Then we say here each linear variation of the force with the same maximum and the same total duration leads to the same final speed. Okay. That is means here, if we look here, okay, when we reach the F bar here with this period time, yeah, when you have the reached maximum, it's here, or it's here, or it's here, yeah, this will lead to the same velocity. Then we imagine now we have the particular case where the force is constant, okay? Then it means now, if we like the principle of momentum, okay, what we have here, we have F, we take it out of the integral as it's time independent, yeah. Then we have here F multiplied by T1 minus T0, the actual time, the initial time T0, okay. Then it means if we look here for the expression of the momentum or the principle of momentum, in our case here, this integral will be equal to this one, okay? Then it means here the left-hand side will be F multiplied by T1 minus T0. Now for the integral of the right-hand side, then it means now if we return back to the general case, yeah, we have this relationship. Okay. Now, this is the general equation. Okay. Now it's depend if the mass is time dependent or it's time independent. Yeah. Now, if it's time dependent, in this case for the mass m, which is equal to mt, it's time dependent, and in this case we have m1 v1 minus m0 v0. Okay. For the case of the mass m, it's constant. Okay. In this case, we have mass multiplied by V1 minus V0. Okay. Now we have the case where the force is equal to zero. Okay. There is no force acting on the particle. This is, we call it the principle of conservation of momentum. That it means the momentum, yeah, will not change during the time. Then we say the momentum at the actual position, it's only m1 v1 and will be equal to the momentum at the initial position. Okay, and this is valid for m. Okay, where the mass m is time dependent. Okay. Now we say principle of momentum provided by simple way the final velocity at time t1. Okay. This principle of momentum provides no acceleration or equation of motion. Okay. It's used advantageously when the force variation is difficult to determine or unknown. Okay. There is anti-action force. F is the force in the system. That means we have action which is equal to reaction. Now, if we look at the representation of the components of the momentum, okay, if we look, for example, this in the system X, Y, okay, we have, for example, here the velocity in X direction, and we have the velocity in Y direction, okay. The force also can be decomposed, yeah, into two parts, which is here the forces along X direction and the force along Y direction. Then it means we can decompose also, yeah, the momentum. Here, there is the two components, the momentum along X direction, which is only the mass multiplied by the velocity along X direction, and the momentum along Y direction, which is the mass multiplied by the velocity in Y direction. Okay. Now, the components of the momentum can be positive or negative. Means here, when the mass m moves along x direction, okay, in the same direction as x, yeah, and that is the case where, okay, the mass m moves against, yeah, or opposite to x direction. In this case here, Vx will be V as it's in the same direction as X, and the Bx will be M multiplied by V. The second case, Vx is opposite to X, okay, it will be taken with minus, and in this case, the momentum will be negative. If we take in this case here now,